Welcome to this explainer. Today, we're diving straight into the fascinating, utterly chaotic world of free radicals. We're going to figure out exactly how these tiny, invisible chemical rebels actually drive so much of the chemistry happening all around us, literally every single day.
Have you ever wondered why that stick of butter left out on the counter spoils and goes rancid? Or, on a totally different scale, how our own bodies utilize atmospheric oxygen just to survive? Well, to understand these everyday phenomena, we've got to look closely at the invisible chemical culprits driving these reactions, and it all comes back to one very specific, highly reactive chemical intermediate.
Meet the free radical. By definition, this is a reactive intermediate characterized by having one or more unpaired electrons. Think of it like a solo dancer, right? Just desperately seeking an electron partner. Because it's missing that crucial pairing, it becomes incredibly reactive. It's paramagnetic, and, fun fact, these radicals are often deeply, vividly colored when they're hanging out in solutions or solid states.
So, here's our game plan for today. First, we just met the free radical. Next, we'll look at generating these reactive intermediates. Then, we'll cover the shape of radicals. And finally, we'll wrap up with their stability and survival. All right, let's jump right into Section 1, generating reactive intermediates, or basically, the birth of a radical.
To achieve this sort of amicable chemical divorce, a process known as homolytic cleavage, where each fragment walks away with exactly one electron, chemists basically rely on three primary methods to break those bonds. We've got photolysis, which uses light energy, thermolysis, which uses intense heat, and redox reactions, which rely on electron transfer.
Let's look at photolysis first. By matching a blast of radiation to a covalent bond-specific energy, we can just snap it apart. For example, if you take a chlorine gas molecule and hit it with light at exactly 487.5 nanometers, it perfectly matches the 244 kilojoules per mole needed to split it. The bond snaps, neatly dividing the molecule into two highly reactive chlorine radicals. Pretty cool, right?
Now, what makes photolysis so incredibly powerful is its precision. It's like a chemical scalpel. If we hit acetone vapor with a very specific 320 nanometer light, it perfectly cleaves just the methyl carbonyl bond. It leaves the entire rest of the molecule totally intact, producing one methyl radical and one acetyl radical.
Alternatively, we can crank up the temperature with thermolysis. This uses heat to break naturally weak links. Take benzoyl peroxide. It contains a famously weak oxygen-oxygen bond. And why is it so weak? Well, it's because of the intense repulsion between the partial negative charges on those adjacent oxygen atoms. It's literally like forcing two negative magnets together. Add a little heat and boom, that bond easily snaps, releasing carbon dioxide and spawning some highly reactive radicals.
Heat is also super effective on azo compounds, like AIBN. In this case, the incredible driving force to generate radicals isn't just a weak bond. It's the formation and release of extremely stable nitrogen gas as a leaving group. That molecule is basically begging to release the nitrogen, making it just a fantastic, reliable source for generating free radicals at relatively moderate temperatures.
Moving on to Section 2, the shape of radicals, where we'll compare planar versus pyramidal structures. What's truly fascinating here is the stark physical contrast. Take a simple methyl radical. It lays completely flat in a planar sp2 hybridized shape. But then look at the CF3 radical. It actually pops up into a rigid sp3 hybridized pyramid. Why the difference? It's because those bulky electron-heavy fluorine atoms strongly repel each other. So, to minimize that repulsive interaction, the entire molecule physically distorts itself into a pyramid.
And here's why that matters. Shape dictates chemical destiny. A flat, planar shape allows new bonds to form from either side equally, meaning if it attacks another molecule, it leads to a racemic mixture, a 50-50 mix of products. But rigid bridgehead radicals, which are trapped in that locked pyramidal configuration, well, they are going to yield entirely different optically active results.
And that brings us to our final section, stability and survival, exploring lifespans from mere milliseconds to practically indefinitely.
Let's crunch some numbers. When we look at the bond dissociation energies required to form different carbon radicals, a really striking trend jumps out. Breaking a primary carbon-hydrogen bond takes 410 kilojoules per mole. A secondary takes 372. But a tertiary carbon-hydrogen bond, that only takes 360. So it clearly takes significantly less energy to create a tertiary radical than it does a simple methyl or primary radical.
That data essentially builds a clear hierarchy, a strict staircase of stability.
We climb from the least stable methyl radical up through primary, secondary, and finally arrive at the highly stable tertiary radical. This whole ladder is primarily driven by the inductive effect. Basically, neighboring alkyl groups donate their electron wealth to that electron-deficient carbon. They act like a tiny support system, stabilizing that lonely unpaired electron.
But you know what the ultimate survival trick is? Resonance. Radicals situated right next to double bonds, like allylic and benzylic radicals, will stay completely flat. They intentionally maintain that planar geometry just to maximize p-orbital overlap. This allows the heavy burden of that single unpaired electron to be shared and delocalized across the entire molecular structure, which drastically increases the radical's lifespan.
And resonance delocalization can be so incredibly effective that certain complex nitrogen-based radicals defeat the norm entirely. Take the 1,1-diphenyl 2-picryl hydrazil radical. Now that's a mouthful, but it is so well supported by its surrounding structure that it becomes completely stable. In fact, it's stable enough that you can literally crystallize it from various solvents, put it in a jar, and just store it safely on a shelf. A literal jar of radicals!
Which leaves us with a totally fascinating paradox to ponder as we wrap up this explainer. How can the universe's most eager, bond-breaking molecular intermediates, molecules that are literally defined by their chaotic, desperate search for an electron, also exist under the exact right circumstances as perfectly stable crystals? Well, it just goes to show that with the right structural support, electron donation, and geometric shape, even the most chaotic chemical rebels can become perfectly peaceful creations. Keep questioning the chemistry around you, and thanks so much for joining me today.